This screencast goes with your handout from Chapter 7. The second half of the handout has two problems. The first half has two derivations of equations. One of those equations, which I'm going to show you how it comes to be, is from page 199 in your textbook, and then the other equation I'm going to derive is on page 205. So imagine that we have a circle in a plane, and that's this circle right here. And we have something that is spinning in the clockwise direction around the center, like that. So I'm going to redraw that. We're going in this direction like this around the center. So at position A, we have some initial velocity. At position B, we have what we're going to call our final velocity, at least at that point. And they're separated by some angle theta. The radius, of course, remains constant. Now, if we take the initial velocity and we put its equation, the vector for that initial velocity down here, same direction, same length, and then we take the final velocity vector after the rotation through angle theta and we put it down here, same magnitude, same direction. This vector right here represents my centripetal velocity. Even though these two vectors are the same length, they do not represent the same quantity because they're pointing in different directions. And that difference is the centripetal velocity, v sub c. Now, you'll notice we now have a triangle made up of velocity vectors. And up here, we also have a triangle made up of length vectors, right here. So we're going to make these two triangles equivalent. In other words, they have the same angle, and the two radii are the same, just like VI magnitude equals VF magnitude. So the triangles are similar. And so we can say that my centripetal velocity, which is down here, VC, is to my initial velocity, right there, as in the upper triangle, pictured in orange, we have chord AB, which is this curved area, which is opposite of theta, just like centripetal velocity is opposite of theta, and then it's over the radius r. These two triangles are approximately similar because, of course, chord AB is a curved line, not a straight line. However, as theta gets smaller and smaller, we can say that the length of chord AB is going to approach a straight line, which we can call delta D, the distance from A to B. So that's what we do down here. We have my centripetal velocity divided by my initial velocity in the triangle down here is to my delta D over my radius, which is the triangle up here. Now, the next thing we recognize is that initial velocity equals final velocity, so let's just use the letter V. And we also know that change in distance equals velocity times the change in time, because we know that velocity equals the change in distance divided by the change in time. And so we're going to substitute that in for delta D. Now, the next thing we're going to do is we're going to move my velocity part, the delta T part, we're going to move that down to the bottom, and we're going to move the velocity up to the top by multiplying both sides by V and dividing both sides by delta T. And now we have this equation right here. Now we know that the centripetal velocity divided by the change in time is called my centripetal acceleration. So my centripetal acceleration equals v squared over r. And this was one of the equations at the very top of page 199. Now if we multiply both sides of the equation by m, we get this equation right here. The centripetal force equals mv squared over r. And that particular equation you used later on in your in the chapter in some of your homework problems. Now let's look at the second circle. This time we have a circle that is in a vertical plane. So imagine that I'm in the middle and I have a string or rope with some masses at the end, or washers or rubber stopper or something, and I'm swinging it over my head and then down near the floor. And I'm going faster and faster around and around in circles. Now, eventually, we're going to go the other direction. Now let's imagine we begin to slow it down. As we slow it down, the goal is to find the minimum velocity that will keep the string taut. Keep it tight so it doesn't just fall down. That minimum velocity is what we want to look at now. So when we do a vector analysis, we see that my centripetal force at the very, very top is equal to my mass times my minimum velocity squared over r. That's the equation that we just derived up here. And that centripetal force is made up of two forces, the force of tension in the string and the force of weight, pulling it down. That overall centripetal force is the sum of those two. Now at the very bottom, down here, we have our maximum speed. And of course, when we look at our maximum speed, my force of tension is going to be much, much greater when the object that is spinning is rotating very, very fast. And at the very top, there's a very minimum tension, almost zero tension. So I drew my vector bigger, but now my tension vector and my weight vector are acting in opposite directions. So now my centripetal force at the bottom equals mv max squared over r, and that's going to be the difference in the force of tension and the force of weight. Now, as my tension in the string goes to 0, which is at the top of the movement of the weight that is spinning in the vertical circle, whatever that mass happens to be, as that tension goes to 0, we can say that at the very bottom, my centripetal force is equal to the force of weight. And of course, the force of weight is mass times gravity. And so we can say that the mass times velocity squared over the radius, which is going to be the centripetal force, minimum centripetal force, is equal to mg. Now, if we cancel out the masses and we solve the equation for v, we get the square root of r over g. Now, let's imagine that we've got a planet like the Earth, and let's suppose we have a satellite, letter S, that we're going to launch, and we want to know what speed will keep the satellite in orbit about the Earth. If the speed is too fast, the satellite is going to be slingshot into outer space, probably picked up by the gravity of the sun. And if it's too slow, the object will spiral into the Earth and burn up in the atmosphere, and pieces of it might even hit the Earth. So what is that minimum speed? Well, we use this equation right here. The minimum speed is going to equal the square root of the radius times gravity. But there's an important difference. My radius now is going to be the radius of the Earth plus this distance to the satellite. This whole distance here now is going to be r. You have to make sure you add up the distance above the surface of the planet plus the radius of the Earth to get the overall R. And another thing, the gravity out here is going to be different than the gravity at the surface of the Earth. The gravity of the surface of the Earth is approximately 9.80, 9.801, depending upon where you are. But out here, the acceleration due to gravity is going to be significantly less. So you would have to calculate what is that new acceleration of gravity in order to plug it in here so that you can calculate the minimum speed to keep a satellite in orbit. And how you calculate that new value of g at some distance r from the center of the Earth will be shown to you in a later screencast.